Right now, you are completely certain that you are sitting still. The floor is steady. Your cup does not slide across the table. Every sense you have insists that you are at rest. But here is what your senses leave out. At this exact moment, you are spinning at 465 meters every second, racing around the sun at 30 kilometers a second, and being swept around the center of the galaxy at more than 200 kilometers a second all at once. Your entire galaxy is falling toward Andromeda at 500 kilometers a second, while everything around it streams towards something so far away and so well hidden that we can only feel its pull. And underneath all of it, space itself is stretching, carrying the galaxies apart faster and faster every moment. Nothing in the universe is still, and all of it is going somewhere. Get comfortable. Hit subscribe if you're new here, because by the end of this, the stillness you feel tonight will be the last thing you trust, and the question of where all of it is finally going will be the one thing left to answer. Now, let's slowly ease into this. Part 1. The painting that was never still. Look up on a clear night, and the first thing the sky offers you is a promise of permanence. The stars hold their places. The constellations you learned as a child are the same ones your grandparents learned, the same ones traced by people who lived thousands of years before either of you. The moon glides along its quiet path. The planets wander a little, drifting against the fixed stars, but they always return. To the eye, to the patient watcher standing in a field with no instrument but attention, the night sky looks like one enormous painting hung above the world, finished long ago and never touched again. We built our entire understanding of the universe on that painting. If the sky did not move, then surely we did not move either. The ground felt solid. The horizon stayed level. And so it seemed obvious, almost too obvious to question, that the earth must be the still center of everything, and that the sun and the moon and the stars must be the things that turned. The cosmos became a set of perfect circles, wheeling around a motionless world, set spinning by something divine, and kept turning forever in the same unhurried rhythm. This was not a foolish idea. It is important to understand that, because it is tempting to look back and laugh at people who thought the earth stood still. They were not stupid. They were doing exactly what good observers do. They were trusting the evidence in front of them, and the evidence in front of them said, without ambiguity, that the ground does not move and the sky does. The model matched the seasons. It explained the eclipses. It predicted where the sun would rise on the longest day and the shortest. It gave farmers a calendar and sailors a map and priests a clock. For thousands of years, a still earth at the center of a turning sky was not superstition. It was the best available science. And it worked. It also gave something that science is not supposed to give, but almost always does anyway. It gave comfort. There is a quiet reassurance in believing you are standing on the one fixed point in all of creation, the anchor around which the whole luminous machine revolves. The heavens move, you do not. Everything has its place, and your place is the center. That is a soft thing to fall asleep believing, and humanity believed it in one form or another for almost the entirety of its history. Then the painting began to crack. It did not shatter all at once. It came apart slowly, one careful observation at a time over centuries. First, a quiet suggestion that the earth might not be the center after all. Then a man with a small glass tube who pointed it at the sky and saw moons circling another world. Then a mathematician who studied the looping paths of the planets and discovered they did not move in the perfect circles everyone had assumed, but in stretched ovals, obeying laws no one had ever written down. Piece by piece, the stillness drained out of the universe, and something far stranger took its place. Because here is what we know now, and what almost no one before a few centuries ago could have guessed. The universe is not still. It has never been still. Not for a single instant in its entire existence has anything in it been truly at rest. The planets move, yes, but so do the stars. So do the galaxies. So do the enormous gatherings of galaxies that the galaxies themselves belong to. And underneath all of that motion, the very fabric of space is stretching, carrying everything apart in every direction at once. The painting you look up at is not a painting. It is a single frozen frame pulled from a film that is still running, and the film is moving faster than you can possibly feel. That is the part that should stay with you tonight. You feel still right now. The ground is not shaking. The stars are not blurring past your window. Your tea sits calmly in its cup and does not slide across the table. Everything about your immediate experience insists that you are at rest. And every bit of that is a trick of scale, a mirage produced by the simple fact that everything near you is moving along with you, so smoothly and so together that the motion cancels out of your senses entirely. In truth, at this exact moment, you are spinning on a planet that is turning faster than a jet aircraft flies. That planet is racing around the sun at a speed that would carry it from one side of a country to the other in the time it takes to read this sentence. The sun itself is sweeping you through the body of the galaxy at hundreds of kilometres every second. The galaxy is falling toward its neighbour, and all of it, together, is being pulled toward something so far away and so well hidden that we cannot even see it, only feel its grip. You are not sitting still. You have never once sat still. You are being carried, and the only reason it feels like peace is that you have never known anything else. So the old picture of a calm and fixed universe is gone, and we are not going to mourn it because what replaced it is so much more interesting. We have stepped out of a painting and into a story of hidden motion at every scale, from the spin of a single world to the drift of the largest structures that exist. And once you start asking how fast things are moving, a second question arrives close behind it, quieter and far harder to answer. If everything is moving, then everything must be moving towards something. So where, in the end, is all of it going? Before we can stand at the edge of that question, we have to go back to the beginning, to the people who first dared to suggest that the ground beneath their feet was not standing still at all. Part 2. Ptolemy's perfect machine. For more than 1,000 years, the most sophisticated picture of the universe ever built placed the Earth at its absolute centre, and the man most responsible for that picture lived in the city of Alexandria in the 2nd century of the Common Era. His name was Claudius Ptolemy. He was a scholar and a mathematician, and above all, an astronomer. And what he wanted was not a myth or a poem about the sky, but something far more demanding. He wanted numbers. He wanted a model of the heavens that did not merely feel right, but actually predicted where each light in the sky would be on any given night, years in advance. Ptolemy inherited a long and careful tradition. He had Babylonian records of the planets stretching back generations, the patient Egyptian observations of the rising and setting of stars, and the elegant geometric thinking of the Greeks. What he did with that inheritance was monumental. He gathered it, organized it, refined it, and assembled it into a single systematic model of the cosmos, laid out in a work so influential that it would guide astronomers for over 1,000 years. We know it today by the name later scholars gave it, a word meaning the greatest, the Almagest. In Ptolemy's universe, the Earth sat at the very centre, perfectly still and unmoving, and around it everything else revolved in a set of nested spheres. Closest was the Moon. Then came Mercury, then Venus, then the Sun, then Mars, then Jupiter, then Saturn, and finally, enclosing all of it, the great sphere of the fixed stars, turning once a day and giving the world its nights and mornings. Each body was carried on its own transparent, crystalline shell, and the shells turned smoothly around the motionless Earth at the centre of all of it. Beyond the outermost sphere of stars, there was nothing a human being could ever hope to know. This was a thing of real beauty, and it rested on a conviction that ran through all of Greek thought. The heavens were perfect, and the most perfect shape was the circle, the figure with no beginning and no end and no flaw. So the heavenly bodies, being perfect, had to move in perfect circles at perfectly steady speeds. It was not just an astronomical assumption, it was almost a moral one. The sky was the realm of the eternal and the unchanging, and circles were the only motion worthy of it. But the actual sky would not quite cooperate, and Ptolemy was too honest an observer to pretend otherwise. The problem was the planets, especially the bright wanderers Mars, Jupiter, and Saturn. If you track a planet like Mars, night after night against the background stars, most of the time it drifts steadily in one direction. But every so often, it does something that should be impossible in a universe of simple circles. It slows down, it stops, and then it reverses, sliding backward across the sky for weeks before halting again and resuming its forward march. We call this retrograde motion, and to a mind committed to perfect circles around a central Earth, it was a genuine scandal. Nothing moving in a clean circle around us should ever appear to go backward. So Ptolemy did what every great defender of a threatened idea eventually does. He added complexity. To explain the backward loops, he proposed that each planet did not simply circle the Earth. Instead, the planet moved in a small circle, and the center of that small circle moved along a larger circle around the Earth. The small circle was called an epicycle, and the large one the deferent. A planet, in this scheme, was riding a circle that was itself riding another circle. And if you chose the sizes and speeds carefully, this looping within looping could reproduce the backward steps that the real planets traced in the real sky. It was ingenious, and it worked, at least well enough to keep going. But even that was not quite enough. When astronomers compared the predictions against careful measurements, the numbers still drifted out of alignment. So Ptolemy introduced one more device, and this one strained the original beauty of the system almost to breaking. He proposed a special point in space, slightly off-center from the Earth, which later astronomers called the equant. The rule was that a planet's motion looked uniform and steady, not when measured from the Earth, and not from the true center of its circle, but only when measured from this offset imaginary point. It was a clever mathematical trick, and it improved the predictions. But it quietly violated the very principle the whole system was built to honor, because now the heavenly motion was only perfectly uniform as seen from a point that was neither the Earth nor the center of anything. For century after century, this elaborate machine of circles upon circles was polished and preserved and trusted. It shaped calendars and timekeeping. It underwrote astrology and guided religious understandings of the cosmos. It served empires and trained scholars and answered, with real practical success, the question of where the lights in the sky would be tomorrow and next year. It was, by any fair measure, one of the longest-lived scientific theories in human history. And yet, underneath all that success, the cracks never fully closed. Every time the observations sharpened, the model needed another adjustment, another small circle, another careful offset, until the whole structure groaned under its own intricacy. Some observers began, quietly, to wonder whether all this complexity was the sound of a correct theory being refined or the sound of a wrong assumption being propped up. A few began to ask whether there might be a simpler explanation hiding underneath, one that did not require the heavens to perform such complicated gymnastics just to go around a motionless Earth. And one of those people, working alone and in no hurry to be noticed, was about to move the center of the universe and never move it back. Part 3. The Priest Who Moved the Sun. The book that began the unravelling appeared in the year 1543, and its author was not a famous philosopher or a court astronomer. He was a churchman a quiet and careful man named Nicolaus Copernicus, and the title of his work translates as On the Revolutions of the Celestial Spheres. That a priest should be the one to rearrange the cosmos may sound strange to modern ears, but in his time it made perfect sense. The Church was the center of intellectual life in Europe. If you wanted to study mathematics, or astronomy, or philosophy, the Church was where the books were kept and the learning happened. Monasteries and cathedral schools were the libraries and laboratories of the age. Copernicus was born in the part of Europe we now call Poland, and he was the sort of person the word learned was invented for. He studied law and medicine. He worked with economics. He read Greek and Latin fluently, but the passion that ran underneath all of it was the sky. For years, he had been quietly gathering observations, running calculations, and turning over an idea that had taken shape in his mind, an idea that contradicted almost everything he had been taught and almost everything the world around him believed. His idea was simple to state and enormous in its consequences. What if the Earth was not the center? What if, instead, the Sun sat at the middle of everything, and the Earth was just one more planet, no different in kind from Mars or Jupiter, swinging around the Sun once a year like the others? It is hard, from this distance, to feel how radical that was. It did not merely move some dots around on a chart. It took the solid, motionless ground beneath everyone's feet and set it in motion, turning the very floor of human experience into the deck of a moving ship. Copernicus knew exactly how dangerous the idea was, and not only as a matter of science. To displace the Earth from the center was to unsettle a worldview that the religious and political order had been built around for 1,000 years. So he kept it largely to himself. For decades he hesitated, refining his calculations, sharing the idea only with a small circle of trusted correspondents, weighing the cost of speaking against the cost of silence. According to the story that has come down to us, he finally held the printed pages of his life's work only as he lay dying, publishing reluctantly at the very end, as if he had to be beyond the reach of the reaction before he would let the idea loose. What he proposed was more detailed than a simple swap of the Sun and the Earth. Copernicus argued that the Earth itself performed 3 distinct motions. First, it spins on its own axis once every 24 hours, and that daily turning is what makes the Sun and the stars appear to rise in the east and set in the west. We are the ones turning. The sky only seems to. Second, the Earth travels all the way around the Sun once every year, and that great annual loop is what produces the slow march of the seasons and the changing positions of the planets through the year. And third, he described a slow wobble of the Earth's axis, a gradual circling motion that we now connect to the tilt of the planet and the long, slow phenomenon astronomers call precession. These were not idle guesses scribbled on the back of a sermon. Copernicus spent decades constructing detailed geometric models and astronomical tables. He used trigonometry to work out the relative distances of the planets from the Sun. He noticed something that fit his picture beautifully. The planets that appeared to move fastest across the sky were the ones closest to the Sun, and the ones that crawled most slowly were the farthest out. He could order the planets by their speed, and the order matched the distances his model predicted. To a mind looking for an underlying simplicity, that was a quiet thrill, a sign that the Sun-centered arrangement was not just possible, but natural. And yet, for all its conceptual elegance, the Copernican model had a frustrating weakness. It did not actually predict the positions of the planets any better than Ptolemy's ancient machine. In some cases, it predicted them slightly worse. The reason is one of the great ironies of this whole story. Copernicus had moved the Sun to the center, but he had kept one crucial piece of the old worldview entirely intact. He still believed, as everyone had for 2,000 years, that the planets must move in perfect circles. And because real planets do not move in perfect circles, his sun-centered system built on circular orbits, was forced into the same kind of small corrective epicycles that had cluttered the old one. He had found the right center and the wrong shape. So at the moment of its birth, the new picture of the universe was a strange, unstable thing. Conceptually, it was cleaner and more beautiful than what came before, and it placed the sun where it belonged. But practically, for an astronomer trying to predict an eclipse or chart a planet, it offered no clear advantage, and it demanded that you believe the impossible, that the ground beneath you was racing around the sun while you felt nothing at all. It was an idea waiting for evidence. It needed someone to look at the sky with a new kind of eye and bring back proof that the Earth truly moved. That proof was about to arrive, carried by a crude little tube of glass that had been invented, almost by accident, for something else entirely. Part 4. The glass that broke the spheres. The instrument that would finally break the crystalline spheres did not come from a scientist at all. It began as a novelty in the Netherlands, a curiosity assembled by spectacle makers who discovered that two lenses held at the right distance could make a distant church tower leap closer. It was a toy, a trick for amusing patrons and impressing officials, and for a little while that is all anyone thought it was. But when news of this strange Dutch device reached Italy, one man understood immediately that it was something far more important than a toy. His name was Galileo Galilei. Galileo did not invent the telescope, and he never claimed to. What he did was greater in its way. He took the rough idea, improved the optics far beyond anything the novelty makers had managed, and then did the one thing none of them had thought to do. He pointed it at the sky. In the year 1609, he turned his improved instrument upward, and over the months that followed, he saw a series of things that no human being had ever seen, each one a quiet blow against the old picture of a perfect, earth-centered heaven. He looked first at the moon. The ancient view held that the heavenly bodies were perfect and smooth, polished spheres of a purer substance than the corrupt and lumpy earth. But through the eyepiece, the moon was not a flawless pearl. It was a world. It had mountains that caught the sunlight at their peaks, while the valleys below them lay in shadow. It had craters. It had a rough, broken, complicated surface that looked unsettlingly like the ground of the earth itself. The boundary between the perfect heavens and the imperfect earth, a boundary that had stood in human thought for 2,000 years, had just developed its first real crack. Then he turned the telescope toward Jupiter, and there he found something that should not have been able to exist. Strung out near the bright disk of the planet were 4 small points of light. He watched them night after night, and he noticed that they changed position from one evening to the next, sliding from one side of Jupiter to the other, yet never wandering away from it. There was only one honest conclusion. These were moons, worlds in their own right, and they were orbiting Jupiter. Let the weight of that settle the way it settled on Galileo. The entire Earth-centered model rested on the claim that everything in the heavens circled the Earth. And here, plainly visible in the glass, were 4 objects circling something that was not the Earth at all. Imagine the scene as he must have lived it. It is a cold, clear night in the winter of 1610. Galileo stands at his instrument in the dark, his breath clouding in the air, and bends to the small lens. There, swimming in the trembling circle of light, is the bright disk of Jupiter, and beside it those 4 faint stars in a neat little line. He has seen them before. But tonight they have moved again, shifted to new positions along that same invisible line, and he understands now, beyond any doubt, that they are going around the planet. He is the first human being in all of history to watch one world circle another world that is not the Earth. There is no announcement, no audience, just one man in the cold with a tube of glass, holding in his mind a fact that quietly ends the ancient universe. The heavens have other centres. We are not the pivot of everything after all. Then he looked at Venus, and that observation sealed the case. Galileo watched Venus over time and saw that it went through phases exactly as the moon does. Sometimes it showed as a full bright disk, sometimes as a thin crescent, cycling through the shapes in between. This was the decisive clue, because the two competing models of the cosmos predicted different things. If Venus circled the Earth, you could only ever see it lit in one limited way. But if Venus circled the Sun, and the Earth circled the Sun as well, then the changing geometry between the three would produce exactly the full set of phases that Galileo was seeing. That little glowing point in the evening sky was carrying a message, and the message was that Copernicus had been right. Venus goes around the Sun. But Galileo, for all his genius with the telescope, was not the one who finally cracked the mathematics of the moving heavens. That task fell to a very different kind of mind, a man who was painfully precise, intensely religious, and, at first, did not even believe in the Copernican idea he would end up proving. His name was Johannes Kepler, and he had access to a resource even more valuable than a better telescope. He had data. He had inherited the life's work of Tycho Brahe, the last and greatest of the astronomers who measured the heavens with the naked eye, a Danish nobleman who had spent decades building enormous instruments and charting the positions of the planets with a precision no one had ever achieved before. Kepler set himself the problem of the planet Mars, and Mars very nearly defeated him. Of all the planets, Mars traces the most stubborn and irregular path, speeding up and slowing down and looping across the sky in ways that refuse to fit a clean circle. For years, Kepler tried to force Tycho's superb measurements into circular orbits, because circles were what everyone assumed, what philosophy demanded, what the heavens were supposed to obey. And for years the numbers refused, missing the observations by a small but absolutely unacceptable amount. Finally, after exhausting every circular possibility, Kepler did the bravest thing a scientist can do. He stopped forcing the data to match his assumption, and he let the data tell him what shape it actually wanted. What it wanted changed everything. Kepler discovered that the planets do not move in circles at all. They move in ellipses, in stretched ovals, with the Sun sitting not at the centre, but at one of the two focal points of the oval. That was his first law, and it quietly executed 2,000 years of perfect circles. Then he found a second pattern. A planet does not move at a steady speed. It sweeps faster when it is closer to the Sun, and slower when it is farther away, in such a way that the line connecting the planet to the Sun always brushes out equal areas of space in equal stretches of time. And finally, he found a third law, the one that tied the whole system together, a precise mathematical relationship between how long a planet takes to orbit and how far it sits from the Sun. Together, Galileo's telescope and Kepler's three laws did something the old world had thought impossible. One gave humanity new eyes to see that the universe was not what it appeared, and the other gave it the exact mathematics to prove it. Copernicus had lit the fire, Galileo had fed it. Kepler had built the framework that finally made it stand. But a question still hung in the air, unanswered. The planets moved, yes, in ellipses, at changing speeds. But why did they move at all? And what invisible hand kept them from simply flying away into the dark? Part 5. The Name of the Pull. The next great step did not come from a new instrument or a sharper measurement. It came from a question that the old astronomers had never quite dared to ask out loud. Kepler had described how the planets move, with a precision that bordered on the miraculous. He could tell you the shape of every orbit, the changing speed of every planet, the exact relationship between distance and the length of a year. But description is not explanation. Kepler could tell you what the planets did. He could not tell you why they did it. Why do the planets move at all, instead of sitting still? What holds them in their orbits, year after year, century after century? Why do they not simply fly off in a straight line into the dark, or fall inward and crash into the Sun? Something had to be reaching across all that empty space and holding the whole system together, and no one had a name for it. The man who gave it a name was Isaac Newton, and the story that has come down to us, whether or not it happened exactly as told, captures the leap perfectly. Newton watched an apple fall from a tree, and instead of seeing an ordinary event, he saw a question that connected the ground to the sky. The apple falls toward the earth. We all know that, but Newton asked something stranger. The moon also, in a sense, is always falling toward the earth, curving around it instead of flying off in a straight line. What if the force that pulls the apple down and the force that holds the moon in its orbit are not two different things at all? What if they are the same single force, reaching from the earth to the apple and from the earth to the moon, and by extension from the sun to every planet that circles it? Newton took that intuition and turned it into one of the most powerful ideas in the history of human thought. He called the force gravity, and he wrote down a law that described exactly how it works. Every object with mass, he said, pulls on every other object with mass. The more massive the objects, the stronger the pull between them. And the farther apart they are, the weaker that pull becomes, fading in a precise mathematical way as the distance grows. It is a law of breathtaking simplicity and almost unbelievable reach. The same equation that governs a falling stone governs the orbit of a planet, the path of a comet, and the slow swing of a moon around its world. For the first time in history, the heavens and the earth obeyed one set of rules. And those rules did something the older models never could. They explained the speeds. Using Newton's law of gravity, you can calculate not just the shape of an orbit, but how fast a body must travel to hold it. The answers match reality with stunning accuracy. The Earth, it turns out, sweeps around the Sun at roughly 30 kilometres every second, which works out to nearly 107,000 kilometres an hour. Try to feel the size of that. You are, at this very moment, moving around the Sun many times faster than any bullet, faster than any spacecraft humanity has ever launched from its surface, and you feel nothing, because the Earth carries you and its air and its oceans all together in one smooth, silent rush. The same law explains why the inner planets move faster than the outer ones. Mercury, hugging close to the Sun where the gravitational pull is fierce, races around at about 47 kilometers every second. It has to move that fast. If it slowed, the Sun's gravity would drag it inward. The Earth, farther out where the pull is gentler, needs only 30 kilometers a second to hold its path. Mars, farther still, moves more slowly again. Everything fits into one clean pattern. The closer a planet rides to the Sun, the stronger the grip on it, and the faster it must run to keep from falling in. Newton's mathematics did not just allow this arrangement, it demanded it. The order of the solar system was no longer a mystery to be marvelled at. It was a consequence to be calculated. This was a genuine turning point in how human beings understood their place in things. For the whole of history before it, the motion of the heavens had been the domain of the gods, or of perfect crystalline spheres, or of forces too holy and remote for ordinary understanding. Newton brought all of it down to earth, quite literally. The same gravity that pulls a raindrop from a cloud holds the planets in their courses. There was no longer one set of laws for the sky and another for the ground. There was just nature, one and the same everywhere, describable by mathematics that a careful human mind could actually grasp. The great cosmic mystery of why the planets move, and how fast, had been answered in a single word: gravity. It would have been easy, standing in that moment of triumph, to believe the picture was finished. The Sun sat at the centre. The planets traced their elliptical paths around it, held by a force now named and tamed and reduced to equations. The mathematics worked to extraordinary precision. It would soon be used to predict the existence of planets no one had yet seen, simply from the way their gravity tugged on the orbits of others. A person living in that confidence could be forgiven for thinking that the architecture of the universe had finally been mapped, that all that remained was to fill in the details. The sun was the still point. Everything turned around it. The story seemed complete. But there was a quiet assumption buried inside that confidence, and it was about to come undone exactly the way the last one had. The whole new picture rested on the sun being the fixed center, the unmoving anchor that the planets revolved around. The Earth had been dethroned, yes, but only to crown the sun in its place. And as astronomers built better instruments and looked harder at the stars, a suspicion began to grow that would repeat the entire revolution all over again, one level higher. Because the sun, the thing everyone now assumed was standing perfectly still at the center of creation, was not standing still at all. It was moving. The only questions were how fast, and toward what. Part 6. Even the sun is adrift. After Copernicus and Galileo and Kepler and Newton had finished their work, the sun inherited the throne the earth had lost. The cosmos no longer revolved around us. Now it revolved around the sun. And for a few comfortable centuries, that new arrangement settled into place and hardened into common sense. The sun became the anchor, the one truly stationary thing, the bright and steady center that everything else moved around. People had given up the idea of a motionless earth, but they had simply transferred all that stillness onto the sun instead. It felt like progress, and in a way it was. But it was also the same mistake wearing new clothes, and the person who first exposed it was not a physicist or a philosopher. He was a musician. William Herschel was born in Germany and moved to England to make his living as a composer and performer. But he had an obsession that gradually swallowed his musical career, and that obsession was telescopes. He began building them himself, grinding his own mirrors and designing his own optics, and he became so skilled that his instruments outperformed almost anything else in the world at the time. When he turned those telescopes toward the sky, he did not simply admire what he saw, he counted. Herschel wanted to know the shape of the universe, and he set out to find it in the most patient and laborious way imaginable. His method was beautifully direct. If the stars filled the heavens, he reasoned, then their arrangement should tell him something about the structure they belonged to. So he divided the sky into small regions and counted the stars he could see in each one, direction by direction, slice by slice. Over time, those counts began to form a pattern. Some directions held far more stars than others, and the directions with the greatest abundance of stars lined up with that faint, milky band of light that arches across a truly dark sky, the band we have always called the Milky Way. From his counts, Herschel constructed a map, and the shape that emerged was not a sphere and not a random scatter. It was a flattened disk, something like a grindstone, wide and thin, with the sun sitting somewhere near the middle of it. He got some of the details wrong, and it is worth knowing why, because the same obstacle will return later in this story. Herschel had no way of knowing that the space between the stars is not perfectly empty. It is threaded with thin clouds of dust, and that dust dims and blocks the light of distant stars, especially along the crowded plane of the galaxy. Because the dust hid the farthest stars from him, Herschel could not see how far the disk truly extended, and he placed the sun near the center, largely because the dust made the star counts look roughly the same in every direction along the band. But set the errors aside and look at what he achieved. Working alone with homemade instruments in the late 1700s, Herschel had discovered that the stars are not scattered at random across an infinite void. They belong to a structure. They form a system, a single enormous disk of stars, and we live inside it. That realization carried a quiet and unsettling implication, and it would take another century for someone to chase it all the way down. If the Milky Way has a definite shape, then it has an orientation, a geometry, a layout. And if it has a layout, then everything in it, including the Sun, has a particular location within it, and, quite possibly, a particular motion through it. The moment you accept that the stars form a structured system rather than a fixed backdrop, you are forced to ask a destabilizing question. How do you know what is moving and what is standing still when you yourself are sitting on a planet, circling a star, embedded in a disk that might be turning, looking out at other stars that might be moving too? Everything you see from here, from one moving platform, looking at other, possibly moving things. How can you ever untangle real motion from apparent motion? This is where a simple thought experiment becomes the key to the whole problem, and it is one you have lived through yourself. Imagine you are sitting in a train, stopped at a station, sipping a drink and looking idly out the window. On the next track over, another train sits beside yours. Then, slowly, that other train begins to slide backward past your window. Except, for a moment, you genuinely cannot tell. Is the other train moving backward, or has your own train begun gliding forward? Without a glance at the solid platform or the ground, there is no way to know from inside. Your own motion and the other train's motion produce exactly the same view. This is what physicists mean by a frame of reference, and it sits at the absolute center of understanding cosmic motion. From inside the train, everything feels still. Your drink rests calmly. The world outside seems to do all the moving. Yet to a person standing on the platform, you are the one flying past at speed. Both descriptions are correct, because motion is not absolute. It is always measured relative to something else. Now place that puzzle on a cosmic scale. Your only window onto the universe is from inside a moving train on a spinning planet, circling a star that is itself, as Herschel suspected, very possibly in motion through a turning disk of stars. Untangling what is truly moving from what only appears to move becomes a problem of extraordinary subtlety, and it took a particular kind of patient genius to solve it. That genius belonged to a quiet Dutch astronomer named Jacobus Kapteyn, a man who loved numbers more than fame, and who set out, without fanfare, to measure the motion of the stars themselves. Kapteyn did not have a grand new telescope of his own. What he had was patience and method. He gathered observations from observatories all over the world, from South Africa and Argentina and Australia, compiling the positions and brightnesses of hundreds of thousands of stars. And then he looked for the one thing that could betray real motion. He looked at proper motion, the tiny gradual shifting of stars across the sky over years and decades. These shifts are minute, often a small fraction of a single degree across a human lifetime, but with enough stars and enough careful mathematics, they tell a story. And the story that emerged from Kapteyn's numbers was strange and, at first, baffling. The stars were not drifting in random directions, as you might expect if their motions were just so much chaotic noise. Instead, they seemed to be flowing in two great streams, two general currents moving in roughly opposite directions across the sky, like two crowds passing each other in a square. At first, this looked like a genuine property of the stars themselves, as though the galaxy contained two distinct populations swimming past one another. But Kapteyn thought harder about it, and he came back to the lesson of the train. What if the two streams were not really about the stars at all? What if the apparent split was a reflection of our own motion, the pattern you would see precisely because the sun is moving through the field of stars, so that those ahead and those behind appear to flow in different directions relative to us? It is worth pausing on how strange and how lonely this kind of reasoning is, because it is the same move that runs through this entire story. Kapteyn never left his study. He never flew out beyond the sun to look back and watch it move, because no one can. Everything he learned about the motion of the sun he extracted from the faint, patient drift of starlight gathered by other people at observatories scattered across the world, numbers copied into ledgers, compared and cross-checked and stared at for years on end. And out of those columns of tiny shifts, he reconstructed a fact that no human being could ever directly witness, that the sun and everything bound to it are sliding silently through space. This is what astronomy so often turns out to be, the act of standing in one fixed place, unable to step outside, and deducing the motion of your own platform purely from the way everything else appears to flow around you. It is detective work performed on the entire universe, and the hidden motion of the sun was one of its quietest and most profound solutions. He ran the calculations, and it fit. The pattern made sense only if the sun itself was moving, carrying the whole solar system along with it through the surrounding sea of stars. Kapteyn could even work out the direction. The sun, he found, is drifting toward a point in the constellation Hercules at a speed of roughly 20 kilometres every second relative to the nearby stars. It is not a violent rush. It is a steady, silent gliding through the stellar neighbourhood. But the meaning of it was profound. The sun had lost its stillness, exactly as the earth had lost it centuries before. There was something almost vertiginous in the pattern of it. Every time humanity found a place to stand and called it the fixed centre, that place turned out to be moving too, a deck on a larger and faster ship. First the earth, now the sun. And if the sun was moving, then the obvious next question was the one that would open the door onto a scale almost too large to hold in the mind. The sun is moving, yes. But moving through what? And around what? And as part of what larger turning thing? Part 7. Drawing the forest from inside the trees. To answer that question, astronomers first had to settle an argument about the size of the universe itself, and the argument turned on those faint, blurry smudges of light that dotted the sky, the objects the old astronomers had called nebulae. Some of these were clearly clouds of gas inside our own Milky Way. But a few of them, the ones with a graceful spiral shape, provoked a fierce debate. Were they relatively small and nearby, just another kind of object floating within our galaxy? Or were they something almost unthinkable, entire separate star systems of their own, lying at distances so enormous that the whole Milky Way was just one island among countless others? The question could not be settled by argument. It needed a measurement, and the measurement needed someone with the most powerful telescope on Earth and the patience to use it well. That person was Edwin Hubble, working at the Mount Wilson Observatory with the Great Hooker Telescope, the finest instrument of its day. Hubble focused on the most prominent of the spiral nebulae, the one in the direction of the constellation Andromeda, and in the year 1923 he found inside it a particular kind of star that changed the history of human thought. It was a Cepheid variable, a star that brightens and dims in a steady, repeating rhythm. Thanks to the earlier work of an astronomer named Henrietta Swan Leavitt, that rhythm was a key. Leavitt had discovered that the true brightness of a Cepheid is tied directly to the length of its pulsing cycle, which meant that if you measured how fast such a star blinked, you could calculate how luminous it truly was, and by comparing that to how bright it appeared, you could work out exactly how far away it lay. Hubble made that calculation, and the answer staggered him. The Andromeda Nebula was not a nearby cloud within our galaxy. It was almost unimaginably far away, so distant that it could not possibly belong to the Milky Way at all. It was a separate galaxy, a whole independent city of hundreds of billions of stars, lying across a gulf of space so wide that its light had travelled for millions of years to reach his eye. In one measurement, the universe had multiplied beyond all recognition. The Milky Way was not the whole of creation. It was a single island in a sea, scattered with countless other islands, and beyond Andromeda there would prove to be more galaxies than there are grains of sand on every beach of the earth. That discovery did something subtle and powerful for the study of our own galaxy. You cannot see the Milky Way from the outside. We are trapped inside it, like someone trying to map the shape of a forest while standing at the foot of a single tree, with the trunks blocking the view in every direction. But once Hubble proved that other galaxies existed, astronomers suddenly had something to compare ourselves to. They could look at Andromeda and other spirals from the outside and ask whether our own galaxy had the same features. Did the Milky Way have spiral arms like those? Did it have a central bulge, a flat disk, a surrounding halo of older stars? By using other galaxies as a mirror, we slowly began to understand the shape of the one we live inside. The mapping itself required a kind of seeing that ordinary telescopes could not provide, because the same dust that fooled Herschel still blocked our view across the crowded plain of the galaxy in visible light. So astronomers turned to a quieter messenger. Scattered throughout the galaxy are enormous clouds of cold hydrogen gas, and the neutral hydrogen atom gives off a faint, natural radio signal at a wavelength of 21 centimeters. That radio whisper has a wonderful property. It slips straight through the dust that stops visible light. So by tuning into it, astronomers could map the gas of the galaxy through obstacles that no optical telescope could pierce. Tracing that signal across the sky, they began, slowly, to draw the spiral arms of the Milky Way from the inside, sketching the shape of the forest while still standing among its trees. Settle into this part of the story, because it is the slow, patient work at the calm center of everything that follows. Picture astronomers across decades, tuning enormous radio dishes to that single faint frequency, listening to the cold hydrogen glow of clouds thousands of light years away, building up the map of our galaxy, one careful measurement at a time. There is something gentle about it, this act of reconstructing the whole shape of your home by listening to its faintest radio murmur, working outward in the dark, piecing together a structure you can never step back far enough to see whole. And the picture that emerged was a grand spiral, a turning pinwheel of stars and gas, with our sun riding far out in one of the lesser arms, a feature astronomers call the Orion Spur, partway between the center and the edge. Let yourself sink into what that orbit actually means, slowly, the way you might drift toward sleep. Imagine you could float free of the Earth and the Sun and look at our place in the galaxy from far enough away to see it whole. You would find yourself far out toward the edge, some 30,000 light-years from the center, riding along on the Orion Spur, one minor arm of the Great Spiral. And you would be moving, all of you, the Sun and its planets together, sweeping around that distant center at more than 200 kilometers every second. It is a speed almost impossible to feel the shape of. In the time it takes to draw a single slow breath, you and everything you have ever known have traveled hundreds of kilometers around the galaxy. And yet there is no wind, no sensation, no blur, because every star around you is carried along in the same great current, all of you turning together so smoothly that the motion erases itself from your senses entirely. One full turn around the galaxy takes about 225 million years, a span so long that the last time the Sun occupied the place it sits in tonight, the earliest dinosaurs had not yet appeared on Earth. We have made the trip only a couple of dozen times in the entire life of the Sun. You are on a journey so enormous that a single lap outlasts whole chapters in the history of life, and you will never feel a thing. Then came one of the largest leaps of all, an instrument that turned the entire Western Hemisphere into a single eye. It is called the Very Long Baseline Array, and it is not one telescope but 10 radio antennas spread across thousands of kilometers, from Hawaii to the islands of the Caribbean. By combining the signals from all 10 dishes and timing them with extraordinary care, astronomers can make them behave as though they were a single instrument the size of a continent. The result is a sharpness of vision almost beyond belief. The array can detect motions in the sky so small they are measured in millionths of a single arcsecond, a precision often compared to spotting a coin resting on the surface of the moon and watching it inch across. With that impossible sharpness, astronomers tracked natural cosmic beacons scattered through the galaxy, intense radio sources called masers, which glow from the gas clouds surrounding newborn stars. These masers act like lighthouses, bright and compact, and locked to specific places in the galaxy's structure. Over years of observation, astronomers watch them creep across the sky, measuring both their proper motion, that sideways drift, and their radial velocity, the speed at which they approach or recede, revealed by the shifting of their light. Combine those two measurements, and you get the full three-dimensional motion of each beacon, not just left and right, but toward and away, the complete dance laid bare. And what that dance revealed, once and for all, was the motion of the galaxy itself. The Sun, it turns out, is not merely drifting toward Hercules at a leisurely 20 kilometres a second. It is sweeping around the centre of the Milky Way at well over 200 kilometres every second, fast enough to circle the entire Earth in a single minute, carrying the whole solar system on an enormous orbit that takes roughly 225 million years to complete just once. We call that span a galactic year. The last time the Sun was in its present position, the first dinosaurs had not yet walked the Earth. And every star you have ever seen is doing the same thing, wheeling around the same distant centre, all of us turning together so smoothly that not one of us can feel it. But that raised the strangest question yet. If the entire galaxy is turning, then it must be turning around something. What sits at the centre of all that motion? Part 8. The Dark Anchor. When astronomers used their new tools to study how the galaxy turns, they found something that did not fit, and the misfit pointed toward one of the strangest objects in existence. The first clue was in the way the rotation worked. If the Milky Way spun like a solid object, like a wheel or a record on a turntable, then every star would share the same angular motion, the inner ones and the outer ones all sweeping around together, keeping their formation like spokes in a wheel. But that is not what the stars do. A Dutch astronomer named Jan Oort, studying the motions of stars near the Sun, found that the galaxy does not turn like a solid wheel at all. It turns more like a whirlpool. The stars near the centre race around quickly, and the stars farther out move more slowly, each at its own pace, the whole structure shearing and winding as it spins. Oort worked out the mathematics of this uneven differential rotation, and from it he could calculate where we sit and how fast we move. He placed the Sun roughly 30,000 light-years from the centre of the galaxy, sweeping around it at a tremendous speed, confirming the enormous orbit that the maser measurements would later pin down with such precision. The galaxy was not a rigid thing turning as one. It was a living, winding spiral, every part of it moving at its own rate, held together not by any solid structure, but by gravity alone, reaching across the immense distances between the stars. But as astronomers tracked the motions closer and closer to the very centre of the galaxy, they ran into something that did not add up, and the size of the discrepancy was alarming. The objects nearest the core were orbiting at ferocious speeds, whipping around far faster than anything farther out. According to the law Newton had written down centuries before, such high speeds required an enormous concentration of mass at the centre to supply the gravity holding those fast orbits in place. And when astronomers added up all the visible matter near the core, all the stars and gas and dust they could actually see, it fell hopelessly short. There was nowhere near enough visible material to generate the gravity those blistering orbital speeds demanded. Something massive and invisible was sitting at the centre of the galaxy, anchoring the whole turning structure, and it was giving off almost no light at all. All of that motion, all of that careful mathematics, all of those precise measurements of stars and masers whipping around the core, pointed to one small region of the sky, a compact and curious radio source lying in the direction of the constellation Sagittarius. In visible light, there is little to see there, just a haze of stars and dust like anywhere else along the crowded galactic plane. But in radio wavelengths, that one spot blazes. Astronomers named it Sagittarius A star, and they trained the Very Long Baseline Array and other instruments on it, watching the stars in its immediate neighborhood swing around it on tight, fast orbits, the way planets swing around the sun, only faster and tighter and around something far darker. From the orbits of those stars, astronomers could weigh the unseen object at the center, the same way you could weigh the sun by watching how the planets move around it. The answer was astonishing. Whatever sits at the center of the Milky Way carries the mass of more than 4 million suns, and yet it is squeezed into a region of space smaller than the orbit of Mercury. Hold those two facts together, because their combination is what makes the conclusion inescapable. More than 4 million times the mass of the Sun, packed into a volume smaller than the inner solar system, emitting almost no light. There is only one thing known to physics that fits that description, that can be so massive and so dense and so dark all at once. It is a black hole, a supermassive black hole, and it is the anchor around which our entire galaxy turns. Let that settle for a moment, slowly, the way it deserves. Everything you have ever seen in the night sky, every star, every constellation, the whole luminous band of the Milky Way itself, is wheeling around a single dark point in the direction of Sagittarius, a point that swallows light and gives back almost nothing. 100 billion stars and more, with all their planets and moons and clouds of gas, the entire spiral pinwheel of our galaxy, all of it held in motion by the gravity of an invisible object 4 million times heavier than the Sun. The center of our world, the thing every star, including ours, is forever falling around, is not a blazing core of light. It is a region of perfect darkness, sitting quietly at the middle of all that brightness, barely flickering while 100 billion suns swirl around it. There is something almost unbearably strange about the quietness of this object. We tend to imagine the center of the galaxy as a place of violence and blaze, and in some galaxies the central black hole does roar, swallowing matter and flinging out brilliant jets across the cosmos. But our own central black hole is, for the moment, calm. It sits there at the focus of everything, dark and nearly silent, sipping only occasionally at the gas and stars that stray too close, while 100 billion suns wheel patiently around it. It does not announce itself. If you went looking for the center of the galaxy with your eyes alone, you would find only stars and dust, and you would never guess that hidden among them is a single point containing the mass of 4 million suns. The most important object in the structure of our galaxy, the gravitational anchor that organizes the motion of everything we have ever seen in the night sky, gives off almost no light at all. We found it not by seeing it, but by watching what it does to everything around it, the same way we have found nearly every hidden motion in this whole story. And here is the thing that should keep you from getting too comfortable even now. Even with the great anchor identified, we are still not standing on anything fixed. The stars orbit the dark center, yes, but the galaxy as a whole is not a tidy, rigid disk spinning serenely in place. It is twisting and warping and wobbling as it turns. The particular arm we ride on, the Orion spur, gently rises and dips above and below the main plane of the galaxy as the sun travels its long orbit, like a swimmer bobbing slightly up and down while being carried along a current. Nothing here is truly still. Every layer of motion we uncover only reveals another layer underneath it. So, we have followed the motion down a long way now. The Earth spins, and we cannot feel it. The Earth orbits the Sun, and we cannot feel that either. The Sun drifts toward Hercules and sweeps around the galactic center at more than 200 kilometres a second, dragging us with it, and still we feel nothing, because everything around us moves along in the same smooth rush. We have found the dark anchor at the center of it all, the supermassive black hole that holds the galaxy together. It would be natural to think we had finally reached the bottom, the still point at the center of our motion. But the galaxy itself, the whole turning 100 billion star spiral, is not standing still in space. It too is moving, falling through the dark towards something else. And the nearest thing it is falling toward is already visible in our sky, a faint smudge of light that is, very slowly and very certainly, coming straight for us. Part 9. The galaxy is falling. The smudge of light coming toward us is the Andromeda galaxy, and the story of how we learned it is approaching begins more than a century ago with a measurement almost no one knew how to interpret. In the year 1912, an American astronomer named Vesto Slipher pointed his telescope at Andromeda and carefully measured its light, breaking it apart into a spectrum the way a prism splits sunlight into colours. What he was looking for was the telltale shift that motion imprints on light, and he found one, but it ran in the opposite direction from what almost every other galaxy would later show. Andromeda's light was shifted toward the blue end of the spectrum, and a blue shift means one thing. The object is not moving away, it is coming toward us. To understand why that shift reveals motion at all, you have to know about an effect you have heard 1,000 times without thinking about it. Picture a car racing toward you with its engine roaring, and listen to what happens to the pitch as it passes. The sound is higher as the car approaches and drops suddenly lower as it speeds away. This is the Doppler effect, and it happens because the waves of sound bunch up in front of a moving source and stretch out behind it. Light behaves the same way. When something glowing moves toward you, its light waves are squeezed slightly toward the blue end of the spectrum. When it moves away, they are stretched toward the red. By measuring that shift in a galaxy's light, astronomers can read off whether it is approaching or receding and how fast. When astronomers in the 1910s and 20s began applying this trick to galaxy after galaxy, they found something that would reshape the whole understanding of the universe. Almost every galaxy they measured was shifted toward the red. They were all moving away from us, and the farther away a galaxy was, the faster it was fleeing. This was Edwin Hubble's great discovery, and it meant that space itself was expanding, carrying the galaxies apart like raisins in a rising loaf of bread, so that every galaxy sees almost every other galaxy receding. That single insight rewrote our picture of the cosmos. It implied that everything had once been much closer together, and it laid the groundwork for the idea that the universe had a beginning, a moment when all of it was compressed into something hot and dense, the moment we now call the Big Bang. But Andromeda, almost alone among the galaxies, broke the pattern. Its light was blue, not red. It was approaching, not fleeing. At the time, that one direction was nearly all that Slipher could say, a velocity toward us with no fuller picture of the path. But a century later, with space telescopes and supercomputers and the same continent-sized radio arrays that had mapped our own galaxy, astronomers could do far more. By combining decades of precise observation, including the exquisite position measurements of dedicated mapping missions, they tracked not just Andromeda's approach, but its sideways drift as well, piecing together the full three-dimensional shape of its motion through space. And the result confirmed the thing the old blue shift had first hinted at. Andromeda is not going to slide harmlessly past us. It is on a direct collision course with the Milky Way, and we are rushing to meet it. The two galaxies are closing the gap with real speed. Andromeda is moving toward us at something like 110 kilometres every second, which works out to more than 400,000 kilometres an hour. And the Milky Way is not waiting passively to be struck. We are drifting toward Andromeda as well, so that when you fold in the motion of our whole local group of galaxies, the distance between the two giants is shrinking at roughly 500 kilometres a second. They are not passing in the night. They are falling toward each other across the dark, two of the largest objects for millions of light years in any direction, drawn together by the same gravity that holds an apple to a branch. And yet the collision is in no hurry, because space is so enormous that even 500 kilometres a second is a crawl against the gulf that separates us. Andromeda lies about 2.5 million light-years away, a distance of roughly 24 quintillion kilometres, a number so large it stops meaning anything. At their closing speed, the two galaxies will not actually meet for something like 4 to 5 billion years. That is a span of time comparable to the entire age of the Earth so far. So this is not a danger looming over us, not tomorrow, and not in any human or even civilizational sense of the future. It is a slow, majestic certainty unfolding over a timescale that dwarfs the whole history of life on our planet. Now picture the encounter itself, because it is nothing like the violent smash the word collision suggests. Stand on a hill 4 billion years from now, if anyone could, and watch Andromeda fill half the sky. No longer a faint smudge, but a second galaxy spread enormous and luminous overhead. The two great spirals drift into and through each other over hundreds of millions of years. And here is the strange and beautiful part. Almost nothing actually hits anything. Galaxies are mostly empty space. The stars inside them are so far apart that even in a head-on galactic collision, the individual stars sail past one another, with room to spare, like two enormous flocks of birds passing through each other without a single collision. To give you the scale of that emptiness, the average distance between stars in our part of the galaxy is around 4 or 5 light-years, nearly 40 trillion kilometres of nothing between one sun and the next. If a star was shrunk to the size of a ping-pong ball, the next ball would lie hundreds of kilometres away. Two galaxies can pass straight through each other, and almost no star will ever strike another. They simply drift past, like ships crossing a harbour at night. There is a quiet lesson hidden in that emptiness, and it is easy to miss. We use the word collision because it is the closest word we have, but it carries entirely the wrong picture. When you imagine two galaxies meeting, you probably see fire and wreckage, stars smashing into stars, a catastrophe of light. The reality is almost the opposite. The two galaxies are so mostly empty, the stars within them separated by such enormous gulfs of nothing, that the encounter is more like two clouds of smoke drifting through each other than like two cars crashing on a road. Whole galaxies can pass straight through one another, and the odds that any one star strikes another are so small as to be effectively zero. The violence of a galaxy merger is not a violence of impact. It is a violence of gravity alone, patient and bloodless, reshaping the architecture of two great structures over hundreds of millions of years, without any single star ever feeling a blow. The real drama is not collision but gravity, the slow reshaping of two galaxies pulling on each other across the dark. As they pass and pass again, gravity flings out enormous streamers of stars, called tidal tails, long bright ribbons pulled loose from the spiral arms and flung across hundreds of thousands of light-years. The graceful spiral structures unwind and tear apart. The two cores swing past each other, fall back, swing past again, and slowly, over 1 billion years or more, settle toward each other until they merge into a single larger object. It is not a crash. It is a long, patient gravitational dance. And when the dance finally ends, something new is left standing where two spirals used to be. The merged galaxy will not be a spiral at all. It will be a great rounded ball of stars, a single enormous elliptical galaxy, and astronomers have already given the future object a name. They call it Andromeda. Our Sun, if it still burns by then, will likely find itself flung into some new and unfamiliar orbit, farther from the centre, on a wandering path through a galaxy reshaped beyond recognition. But even this enormous event, the merging of our entire galaxy with its nearest giant neighbour, is not the largest motion we are caught up in. Because the Milky Way and Andromeda, together with everything around them, are themselves being pulled towards something larger still, and to see it, we have to pull back our view once more, farther than the mind comfortably goes. Part 10. Groups inside, clusters inside Laniakea. To see what the Milky Way and Andromeda are falling toward, we have to do the thing this whole story keeps asking of us. We have to pull back and widen our view again, past the two great spirals, past the little crowd of galaxies they belong to, out to a scale where entire galaxies become mere points of light in a far larger architecture. Because galaxies do not float alone in the dark, scattered at random like dust. They gather, they clump together, they follow gravity the way water follows the slope of the land, collecting into groups and clusters and structures so enormous that they are among the largest things that exist anywhere. Start small, at least by the standards of what is coming. Our Milky Way belongs to a modest gathering of galaxies that astronomers call the local group, a collection of around 80 galaxies bound together by gravity, spanning something like 10 million light-years across. The Milky Way and Andromeda are the two giants of this little community, each one surrounded by a retinue of smaller satellite galaxies, dim companions that orbit the big spirals the way moons orbit a planet. It is a neighbourhood, a small cluster of homes in the dark, and for a long time you might be tempted to think of it as the basic unit of the cosmos. But the local group is only a single pocket within something far larger. The next step up the ladder is a galaxy cluster, and our local group is just one minor member on the outskirts of a much greater one. Tens of millions of light-years away lies the Virgo cluster, an immense gravitational gathering of more than 1,000 galaxies, sitting roughly 65 million light-years from us and pulling on everything around it, including us. And we are not merely sitting nearby, admiring it. Our entire local group is being drawn toward the center of the Virgo cluster, falling toward it through the dark at something like 600 kilometres every second. The crowd of 80 galaxies that contains our entire Milky Way is itself a thing in motion, sliding toward a far greater concentration of mass. But even a cluster of 1,000 galaxies is not the end of the structure. Clusters themselves gather into still larger assemblies, collections of clusters strung together across space, which astronomers call superclusters, the largest known structures in the entire observable universe. These can stretch across hundreds of millions of light-years and contain tens of thousands of galaxies woven together in long filaments and sheets and threads, with enormous empty spaces between them. And the supercluster we belong to has a name as grand as its scale. It is called Laniakea, a word taken from Hawaiian that means immense heaven, and the name is well earned. Laniakea spans more than 500 million light-years and gathers together something like 100,000 galaxies, including the Virgo cluster and other great superclusters, all of them interconnected in a single sprawling web of cosmic flows. How could anyone possibly know such a thing, map a structure so large that light itself takes hundreds of millions of years to cross it? The answer comes back, as it always does in this story, to motion. Over the past few decades, astronomers did not simply chart where galaxies are. They measured how galaxies move, and from the pattern of that movement, they reconstructed the architecture that the movement reveals. To do it, they needed more than the simple red shift of cosmic expansion. They needed to measure what is called peculiar velocity, the genuine motion of a galaxy through space relative to the overall stretching of the universe, the part of its movement caused not by expansion, but by the gravitational pull of everything around it. That measurement is delicate work, because you cannot take a single photograph and read off how fast a galaxy is sliding sideways. You have to combine many techniques, calibrating the true distances to thousands of galaxies and comparing those distances against their redshifts to separate the motion of expansion from the motion of gravity. One powerful method ties a spiral galaxy's brightness to how fast it spins, so that by measuring its rotation, you can estimate how luminous it truly is, and from that, how far away it sits. Gather enough of these distances, fold in the red shifts, and the leftover motion, the peculiar velocity, stands revealed. The great mapping projects, known as the Cosmic Flows Surveys, did exactly this for thousands upon thousands of galaxies, building a three-dimensional map, not just of where the galaxies are, but of where they are going. And what those velocity maps revealed was something genuinely startling. The galaxies were not simply drifting apart with the general expansion of the universe, like dots painted on the surface of an inflating balloon. Layered on top of that expansion was a coherent, organized flow. Galaxies across enormous stretches of space were streaming together in the same direction, leaning toward particular regions, draining toward shared destinations like water, finding the low points of an invisible landscape. It was this coherent flow that allowed astronomers to define Laniakea in the first place, by mapping the watershed of cosmic motion, drawing the boundary of our supercluster along the lines where galaxies stop flowing toward us and begin flowing towards somewhere else. Sit with the scale of this for a moment, because it is the kind of thing that quietly rearranges your sense of where you live. You are on a planet, circling a star, far out on the arm of a spiral galaxy, which belongs to a small group of 80 galaxies, which is falling toward a cluster of 1,000 galaxies, which is one node in a supercluster of 100,000 galaxies, all of it stretching across 500 million light-years, and all of it streaming together toward a common destination. Every home you thought was the whole world turns out to be a single room in a larger house, and that house a single building in a larger city, and the city itself flowing somewhere through the dark. And the most unsettling part is that the destination of all that streaming, the thing toward which 100,000 galaxies are leaning, was at first something astronomers could not see at all. They could only feel its pull, hidden behind the body of our own galaxy, and they gave it a name that admitted exactly how little they understood it. They called it the Great Attractor. Part 11. Toward the Unseen, Away from the Empty. Astronomers first noticed the strange flow back in the 1970s, and it troubled them because it did not fit the simple picture of a universe expanding smoothly in all directions. When they measured the motion of galaxies, including our own, they found that we are not merely drifting outward with the general expansion, we are also moving sideways, with purpose, at hundreds of kilometres every second, and not at random. Whole crowds of galaxies, our own among them, were leaning in the same direction, all streaming toward a single region of the sky, as though something enormous out there were quietly pulling everything toward itself. But when astronomers tried to look directly at the place all those galaxies were heading, they ran straight into an obstacle, and it was an obstacle of our own making. The direction of the flow lies behind the body of the Milky Way itself, behind the crowded, dusty band of our own galactic plane. That region of the sky is so thick with the stars and gas and dust of the Milky Way that it blocks our view of whatever lies beyond, like trying to see a distant mountain through a dense bank of fog directly in front of your face. Astronomers call this blinded region the zone of avoidance, because it is the part of the sky where our own galaxy gets in the way and forces extragalactic astronomy to look at clay. The thing pulling us was hiding behind the very galaxy it was pulling. Still, the motion was undeniable. So astronomers named the unseen source after the only thing they could measure about it. They called it the Great Attractor, not because they could see any object there, but because they could feel its gravitational grip on the motion of galaxies across a wide stretch of the cosmos. Entire clusters were leaning toward it, and our local group, our whole supercluster, was caught in the same current, sliding toward this hidden concentration of mass at roughly 600 kilometres a second. For a while it was one of the strangest situations in astronomy, an enormous gravitational pull from a source no one could actually observe, masked behind the dust of home. Over the following decades, astronomers found ways to see partway through the fog. They turned to instruments that detect wavelengths the dust does not block as easily, using X-ray telescopes and infrared surveys to peer into the zone of avoidance. And bit by bit, the hidden region gave up some of its secrets. They found huge concentrations of mass behind the galactic plane, not a single object, but a whole crowded region teeming with galaxy clusters. One of the largest was a great cluster lying a couple of 100 million light-years away, and it was not alone. It turned out to be part of something larger still, an outlying piece of one of the most massive structures in the local universe, an enormous gathering of galaxies called the Shapley supercluster. The Great Attractor, it seems, is the near edge of a colossal concentration of mass, and the deeper pull comes from the Shapley supercluster beyond it, dragging our whole region of the cosmos toward it across an immense distance. But the picture turned out to be more subtle than a single great pull, and the refinement is one of the most elegant ideas in modern cosmology. In the year 2017, astronomers using the detailed motion maps of tens of thousands of galaxies found that our flow is not only a matter of being pulled towards something massive, it is also a matter of being pushed away from something empty. They identified, on the opposite side of the sky from the Great Attractor, a region of unusual emptiness, a great cosmic void with very little matter in it at all, and they called it the dipole repeller. Now, a void cannot really push anything. There is nothing there to do the pushing. But the effect is real all the same, and it works like this. Gravity pulls galaxies toward concentrations of mass, so a region packed with clusters draws everything around it inward. An empty region does the opposite, in a relative sense. Where there is little matter, there is little pull, so galaxies are not held back on that side and drift more easily away from it, toward the fuller regions on the other side. Imagine you are floating in a slow river. On one side, there is a current drawing you in. On the other side, the water is flat and still, exerting no pull at all. You drift toward the current, not because the still water pushes you, but because nothing on that side holds you back. Our galaxy is caught in exactly that kind of cosmic flow, drifting away from the emptiness of the dipole repeller and toward the fullness of the Great Attractor and the Shapley supercluster beyond it. The push of the void and the pull of the mass working together to carry us along. So even at this enormous scale, the scale of superclusters and cosmic voids, we are still in motion, still being carried by forces we cannot see, leaning across hundreds of millions of light years toward a destination hidden behind the dust of our own galaxy. We have followed the motion up through every level now, from the spin of the Earth to the streaming of the supercluster, and at each level the same truth has held. Nothing is still. Every anchor we reach turns out to be drifting. Every center we find is orbiting something larger. The Earth moves around the Sun around the galaxy toward Andromeda, the local group toward Virgo, and the whole of Laniakea toward the Great Attractor. But there is one more level, and it is the level that finally changes the question. Because when you zoom out, past the clusters and the superclusters, past the filaments and the voids, past the Great Attractor and the Shapley supercluster and everything else that gravity has gathered, a different kind of motion begins to dominate. A motion that does not lean in any one direction, but acts everywhere at once. It is the expansion of space itself, and it does not merely carry the galaxies along. In the end, it overrules everything. The streaming flows, the great attractors, the falling together of galaxies, all of it is local detail painted on top of a far larger and stranger movement. And once you account for that movement, you are no longer asking which direction our galaxy drifts. You are asking the final question, the one this whole journey has been climbing toward. Where is everything, all of it, every galaxy in the universe, ultimately going? Part 12. The question with no comfortable answer. We have followed the Earth as it spins and circles the Sun. We have watched the sun drift through the galaxy like a leaf carried on a current. We have pulled back to see the whole Milky Way falling toward Andromeda, and the local group sliding toward Virgo, and all of Laniakea streaming toward the Great Attractor. It is already almost too much to hold in the mind, this picture of a moving world inside a moving system, inside a moving galaxy, inside a flowing supercluster. But now it is time to ask the largest version of the question, the one that all of this has been building toward. Set aside every local motion, every pull toward this cluster or that attractor, and ask where the whole thing is going. Where is everything in the universe ultimately headed? What, if anything, is the final destination? To even approach that question, we have to talk about something genuinely strange, something that does not glow or shine, something that seems to be pulling the strings of the entire cosmos from behind a curtain, and something so unexpected that it shook physics to its foundations when we stumbled onto it. The story of its discovery begins, fittingly, with scientists trying to predict the end of the universe and getting an answer so wrong, so completely opposite to what they expected, that it rewrote the future of everything. In the 1990s, two competing teams of astronomers set out to measure how fast the expansion of the universe was slowing down. One team was led by Saul Perlmutter, the other by Brian Schmidt and Adam Riess. And both of them assumed, as nearly everyone did, that the answer would be a deceleration. The reasoning behind that assumption was perfectly sound. The universe had been expanding ever since the Big Bang, flinging the galaxies apart. But every galaxy pulls on every other galaxy with gravity, and gravity is attractive. It pulls things together. So, the expansion ought to be gradually slowing, with all that mutual gravity acting like a brake on the flying apart, dragging it down over time. The only real question, everyone thought, was whether the brake was strong enough to eventually stop the expansion and reverse it, or whether the universe would coast outward forever, slowing but never quite halting. To find out, the teams measured a special kind of exploding star, a type of supernova that always detonates with very nearly the same true brightness, which makes it a perfect cosmic mile marker. If such a star looks dimmer than expected, it must be farther away than expected, and by measuring many of them across the universe, the teams could chart exactly how the expansion had changed over cosmic history. The data came back, and it refused to say what everyone expected. The distant supernovae were too faint. They were farther away than they should have been in a universe that was slowing down. The galaxies were not merely receding, their recession was speeding up. The expansion of the universe was not decelerating under the brake of gravity at all. It was accelerating, flying apart faster and faster as time went on, as though some invisible force were stepping on the accelerator instead. Both teams checked and rechecked their work, hunting for errors, because the result was so contrary to expectation that it was hard to believe. But the answer held. In the year 1998, the world of physics had to accept something almost impossible to accept. Something unseen and immensely powerful is pushing the universe apart, and pushing harder all the time. They gave that something a name, and the name is an honest confession of ignorance. They called it dark energy, and the word dark here means exactly what it means for dark matter. We cannot see it, and we do not know what it is, but we know it is real, and we know it dominates the cosmos. Roughly 70% of everything in the universe, of all the energy and all the matter that exists, is this mysterious dark energy. To feel how strange that figure is, consider what it leaves for everything else. Everything you have ever seen or touched or tasted, every star and planet, every atom in your body and in the ground and in the farthest galaxy, all the ordinary matter in existence adds up to less than 5% of the universe. Another quarter or so is dark matter, the unseen mass that holds galaxies together with its gravity. And the rest, the largest portion by far, is this silent force, pushing everything apart. It helps to take a full accounting of what the universe is actually made of, because the inventory is humbling. Everything we have spent this entire journey describing, every planet and star and galaxy, every cluster and supercluster, all the glowing matter and all the dark dust and gas, all of the ordinary material that makes up worlds and bodies and atoms, comes to less than 5% of the universe. Another quarter or so is dark matter, the invisible mass whose gravity we met when we found that the galaxy spins too fast for its visible stars to hold it together. And the remaining 70%, the largest part of reality by far, is dark energy. So the cosmos we can actually see and touch, the part this whole long story has been about, is a thin, bright skin stretched over something far larger and almost entirely unknown. There is one more twist of history worth knowing too. Decades before any of this was measured, Einstein had added a term to his equations of gravity, a kind of constant energy of space, in order to keep the universe from collapsing. When the expansion was discovered, he is said to have called that term his greatest blunder and thrown it away. The discovery of dark energy quietly resurrected the very idea he had discarded, as though the universe had been holding on to his mistake all along, waiting for us to need it. What could dark energy actually be? Here the story becomes humbling, because our best attempt at an explanation produces the worst prediction in the history of science. The most natural idea is that dark energy is the energy of empty space itself. According to quantum physics, a vacuum is not truly empty. Even in perfectly empty space, tiny fluctuations of energy are constantly flickering in and out of existence. So perhaps the energy of all that restless, empty space is what drives the cosmic acceleration. The trouble is the amount. When physicists calculate how much energy empty space should contain, according to quantum theory, and compare it to the amount of dark energy we actually observe driving the expansion, the prediction overshoots the reality by a factor of around 10, followed by 120 zeros. It is the largest disagreement between theory and observation ever recorded, a mismatch so enormous it is almost comical. It is as though you tried to weigh a single feather, and your calculator insisted the feather outweighed the entire Earth. Something is profoundly wrong or profoundly missing in our understanding. Stop and notice how unusual it is, in all of science, to be this certain of a thing and this ignorant of it at the same time. We can measure the rate of the cosmic acceleration with real precision. We can chart how it has changed over billions of years by reading the light of exploding stars across the universe. We can tell you that dark energy makes up roughly 70% of everything, and that it is, slowly, winning. And we cannot tell you what it is. We cannot tell you why empty space should push, or whether that push will hold steady forever or change its mind. It is as though we had learned to predict the tides to the minute without ever discovering the moon, charting the rise and fall with confidence, while the cause of it remained completely hidden. The accelerating universe is the largest fact about our future, and it rests on the largest hole in our understanding. And yet, wrong as our explanation is, the effect itself is not in doubt. Picture the universe as an enormous loaf of raisin bread rising in an oven, with the galaxies as raisins baked into the dough. As the dough expands, every raisin drifts away from every other raisin, and that is the ordinary expansion of space. But now imagine that partway through the baking, something turns the heat up and up again, so the dough does not merely rise, but inflates faster and faster. That extra growing push is dark energy. And here is the truly unsettling property of it. Dark energy is not diluted as the universe expands, the way ordinary matter spreads thinner and thinner as space grows. Dark energy appears to be a property of space itself, so the more space there is, the more dark energy there is. It does not run out, it does not weaken with distance. As the universe grows, the total push only grows with it, which means the acceleration feeds on its own success, getting stronger the larger the cosmos becomes. So this is where the long journey has finally brought us. We followed the motion down from the spin of a planet to the streaming of superclusters, and at the very largest scale, we find that the dominant motion of all is this accelerating expansion, driven by a force that makes up most of reality and that we cannot explain at all. The comforting calm you feel sitting still tonight was always a trick of scale, the smoothness of being carried. And now the calm breaks completely, because the largest scale of all is not gently drifting. It is flying apart, faster every moment, governed by something we have measured precisely and understood not in the slightest. The question of where everything is going finally has the only honest framing it can have. The answer depends entirely on what dark energy does next. And depending on its behavior, the universe faces three very different endings. Part 13. Three doors. If dark energy keeps doing exactly what it is doing now, pushing the universe apart faster and faster without limit, then it leads to one of the most extreme predictions in all of cosmology, an ending that physicists call the Big Rip. To understand how it would work, you have to remember what dark energy is fighting against. In our universe right now, gravity is still winning in all the places that matter to us. Galaxies hold together. Stars orbit their galactic centers. Planets cling to their suns. The expansion of space is real, but inside galaxies and solar systems, the local pull of gravity is far stronger than the gentle push of expansion, so our cosmic neighborhood stays bound together even as the universe as a whole flies apart. But the Big Rip scenario asks what happens if dark energy does not stay constant, if instead it grows stronger over time, intensifying without end. In some versions of the theory, the acceleration itself accelerates, the push increasing until it begins to overwhelm even gravity, even the forces that hold matter together. Picture a car rolling faster and faster down a hill, and then imagine the hill itself growing steeper the farther you go, so the speed climbs without any limit. That is the shape of the Big Rip. At first, you would notice nothing. The galaxy clusters would simply drift apart a little faster than expected. The gap between the Milky Way and Andromeda would start widening too quickly for them ever to meet. But it would not stop there. As the push intensified, the damage would work its way inward through every scale of structure. Eventually, the galaxies themselves would begin to come undone, their stars pulled loose from their orbits and scattered as the expansion grew stronger than the gravity binding them. Then the star systems would dissolve, planets torn from their suns, moons lost into the growing dark, and it would keep going. The force of expansion would grow so overwhelming that it would overpower even the electromagnetic forces that hold solid matter together. Planets would crack apart. Then atoms themselves would be pulled to pieces. And in the final fraction of a second, the expansion would tear into the very protons at the cores of atoms, ripping apart the smallest building blocks of matter as space itself stretched beyond anything any particle could survive. In the last moments before the Big Rip, the universe would become a storm of disassembled fragments, and then nothing but unbound energy flickering in an emptiness with no structure left at all. One model places this ending around 22 billion years from now, but that number is only a single model's estimate, and it could be far sooner or it could never happen at all, because it depends entirely on how dark energy behaves, and that is precisely what we do not understand. Not every possible ending tears the universe apart, though. There is an opposite future, and it begins with a simple question. What if the expansion does not go on forever? What if, at some point, gravity fights back and wins? Early in cosmic history, everything was hot and dense, and space was expanding outward, while gravity pulled inward, trying to slow the whole thing down. That tug-of-war between expansion and gravity has been running since the beginning, and for a long time many scientists thought gravity might eventually triumph. This is the scenario known as the Big Crunch, and in it, the expansion we see today is only a temporary phase. Perhaps dark energy weakens over time, or perhaps it was never truly permanent to begin with. And if it faded, gravity would slowly reassert its grip and begin pulling everything back together. In a big crunch, the great outward motion would gradually halt, stall, and then reverse. The galaxies that had spent billions of years drifting apart would begin, almost imperceptibly at first, to fall back toward one another. The cosmic web would contract. Over enormous spans of time, the universe would shrink, and as everything was squeezed into a smaller and smaller volume, the temperature would climb. The night sky would slowly brighten, not with new stars being born, but with the accumulated light of an entire cosmos collapsing inward. Old stars crushed together as the space between them vanished. The fabric of space-time would bend inward like a closing fist, until in the final moments the entire universe collapsed back into a single, hot, dense point, perhaps ending there, or perhaps rebounding into a new beginning, a fresh expansion rising from the ashes of the old. There is a real beauty to the symmetry of it, the idea that the cosmos might end exactly where it began, that the great expansion might be just one breath in an endless cycle of breathing out and breathing in. But there is a problem with the Big Crunch, and the problem is the data. Everything we have actually observed, all the redshifts of the galaxies and the careful measurements of the cosmic background light left over from the early universe, tells us the same thing. The universe is not slowing down, it is speeding up. Gravity is not winning the tug of war, it is losing, and losing by more all the time. So, unless dark energy changes dramatically and unexpectedly in the future, reversing its push and allowing gravity to take over, the Big Crunch does not seem to be where we are headed. It remains a possibility only because we understand dark energy so poorly that we cannot completely rule out a future in which it behaves in some way we have not anticipated. If anyone ever truly discovers what dark energy is, it will not merely be a scientific breakthrough, it will be one of the most important discoveries in the history of thought, because it would finally tell us which of these endings is real. Until then, we are left with the evidence we can actually see, and the evidence points away from both the violent rip and the fiery crunch, toward a third ending, quieter than either, and in its own way, the most haunting of all. Part 14. The Long Cold. The third ending does not explode, and it does not collapse. It simply continues, on, until everything quietly fades. Physicists call it the Big Freeze, and it is a universe that dies not in fire or violence, but in silence and cold, and an emptiness that keeps on growing forever. And it is, according to our best current evidence, the most likely fate of all. Everything we have measured about dark energy is consistent with it being a constant, a steady property of space that neither grows the way the Big Rip requires, nor fades the way the Big Crunch would need. The careful measurements of the cosmic background light and the great surveys of millions of galaxies all point the same way. Dark energy appears to be holding steady, humming along, gently and relentlessly stretching space at a constant rate. And if that holds true, then the Big Freeze is not merely possible, it is where we are going. Let us follow that future forward, step by patient step. We begin in the present, where the universe is still young and bright and full of activity. Galaxies are close enough together to interact. New stars are being born in glowing clouds of gas. Planets circle their suns, black holes feed quietly at galactic centers, and the cosmic web glows with energy. But time passes, an enormous amount of time. Give it 100 billion years, and the picture changes. The accelerating expansion will have carried the distant galaxies so far away, and pushed them away so fast, that their light can no longer cross the growing gulf to reach us. One by one, they will slip beyond the cosmic horizon and vanish from any possible view, not because they have ceased to exist, but because the space between us and them is expanding faster than their light can travel across it. They will still be out there, but they will be gone forever, like ships that have sailed over the edge of an ocean that never ends. Eventually, every galaxy beyond our own merged remains will disappear in this way. The Milky Way and Andromeda, by then long since combined into the single great elliptical galaxy called Milkomeda, will become an island floating alone in a dark and silent sea, with no other galaxy anywhere in sight. And the lights inside that island will begin, slowly, to go out. Star formation cannot continue forever, because stars need gas to be born, mostly hydrogen, and that supply is finite. As stars live and die, they return some of their material to space, but the recycling is never perfect, and over time more and more of the gas is locked away in dead remnants. Estimates suggest that in roughly 1 trillion years, star formation across the universe will cease entirely. No new stars will ever be born again. There is a strange tenderness in this slow fading, if you let yourself feel it. The universe does not end the way a story usually ends, with a final dramatic event that settles everything. It ends by gently running down, the way a room grows quiet after a long party, the lights dimming one by one rather than all at once. For an almost incomprehensible stretch of time, the dim red dwarfs will keep the dark company, glowing faint and steady long after the bright young stars have burned themselves out, the last small fires in an emptying house. A creature living near one of those final stars, if any could, would look up at a sky almost entirely without other galaxies, the great cosmic web having long since receded beyond the horizon, and would have no way of knowing that the universe was ever full of light. They would see only their own dim sun and a scattering of nearby embers, and they would think that was all there had ever been. The stars that remain will burn through their fuel, one by one. The smallest and coolest stars, the red dwarfs, will last the longest, glowing faintly for trillions of years, the final embers of a cosmos that once blazed with light, but even they must eventually fade. And after the last star gutters out, only the remnants will be left, the cold corpses of stars, white dwarfs slowly cooling, neutron stars, and black holes. This is what physicists call the degenerate era, a stretch of time when there are no living stars at all, no new light anywhere, only cold collapsed objects drifting through an ever emptier dark. And still time keeps going, on a scale that makes everything before it seem like an eye blink. Over something like 10, followed by 40 zeros of years, even the stellar remnants will break down. The white dwarfs will cool until they become cold black dwarfs. The protons that make up ordinary matter may themselves slowly decay, if certain theories are correct, so that the very atoms of those dead stars come apart over unimaginable spans of time. The black holes will last longer than almost anything, but even they are not eternal. Stephen Hawking showed that black holes are not truly permanent. They slowly leak energy through a subtle quantum process, radiating away their mass over time in what we now call Hawking radiation. The process is staggeringly slow. A black hole with the mass of our Sun would take something like 10, followed by 67 zeros of years, to evaporate completely. Let that number sit against the present age of the universe, which is only about 13.8 billion years. The whole of cosmic history so far, every star that has ever shone, every world that has ever formed, all of it has happened in what is, by comparison, less than the first faint instant of the universe's existence. It is almost impossible to hold these timescales honestly in the mind, and it is worth trying anyway, because the trying is its own kind of awe. The universe today is about 13.8 billion years old, and to us that already feels like an eternity beyond comprehension. But against the lifespan of the Big Freeze, the entire age of the universe so far is less than a rounding error, less than the first faint flicker of a candle that will go on burning dimmer and dimmer, for a length of time written not in billions of years, but in ones followed by dozens of zeros. Every event you could ever name, the birth of the sun, the rise of life, the building of every civilization, the whole span from the first star to the last human thought, all of it is crowded into the tiniest sliver at the very beginning of the story. We live in the bright morning of the cosmos, in the brief, warm window when there are still stars to shine and worlds to stand on. Almost the entire future of the universe is darkness, and we happen to be awake for the small lit part at the start of it. Picture the very end of it, the last event of any consequence in the entire history of everything. Trillions upon trillions of years from now, long after the last star has died and the last galaxy has gone dark, a single black hole hangs alone in the cold, the final massive object left in a universe of almost perfect emptiness. And it is shrinking, one whisper of radiation at a time, growing smaller across spans of time so long they cannot be written except as towers of exponents. Then, at the very end, in a final faint flicker, it evaporates completely and is gone. And after it, there is nothing left anywhere that can change. No stars, no planets, no light, only a thin and cooling fog of stray particles, electrons and their kind, drifting apart forever through a space that keeps on expanding. The temperature falls toward absolute zero, not because there is some cold thing somewhere, but because there is nothing left at all to generate any warmth, no fusion, no gravity drawing matter together, just an endless, thinning dark. And here is the thought to carry with you into sleep, because it is the quiet center of this whole long journey. In that final cold, the laws of physics still hold. Gravity still works. The rules that built the galaxies and lit the stars and brought you into being are still there, etched into the empty void, exactly as true as they ever were. But there is no one left to read them, and nothing left for them to do. The universe does not end with a scream or a crash. It ends with a vast, even silence, the laws intact and the lights all gone. Remember how this began, with the night sky that looked to the ancients like a great cosmic painting hung above the world, fixed and finished and perfectly still. We have learned since then that the stillness was never real, that the calm was only ever a trick of scale, that every point of light in that painting was racing through the dark, and that the whole canvas was, all along, going somewhere. Now we know where. Everything in the universe is going toward the cold and the quiet and the slow coming apart of all things. And yet, knowing that, the night sky above you tonight is no less beautiful, only more precious, because you understand at last that you are not looking at a finished painting. You are watching a brief and luminous moment in the middle of the longest story there is, a moment with stars in it and warmth, and you, awake under all of it for just a little while. We have followed the motion from the spin of a single quiet planet all the way out to the slow coming apart of everything that exists, and at every step the same truth has waited for us. Nothing is still, nothing has ever been still, and all of it is going somewhere. We have measured the journey to its farthest end. We still cannot say why any of it is here to make the journey at all, and, perhaps, drifting off beneath those moving stars, that is the most beautiful mystery we will ever be left holding.